A wave is a disturbance that travels through space and time, carrying energy without carrying matter. Imagine dropping a pebble into a still pond. You see ripples spread outward from the point of impact. These ripples are the waves, carrying energy from the pebble to the rest of the pond. Waves are all around us. We see them in water, hear them as sound, and use them to communicate with radio and light. Understanding waves helps us understand the universe around us. The study of waves is a fundamental part of physics, and it helps us understand everything from the smallest particles to the largest structures in the cosmos. Waves are all about oscillations. An oscillation is simply a back-and-forth motion. Think of a pendulum swinging or a spring bouncing. Each complete swing or bounce is one oscillation. Frequency tells us how many oscillations a wave makes per second. We measure frequency in hertz. A wave with a frequency of 1 hertz makes one complete oscillation every second. Period is the time it takes for one complete oscillation. It is the inverse of frequency. A wave with a period of 1 second has a frequency of 1 hertz. Imagine a wave like a roller coaster. The amplitude is the height of the wave from its resting point. A high-amplitude wave on our roller coaster would be a thrilling ride, while a low-amplitude wave would be a calmer experience. The crest is the highest point of a wave, the peak of the roller coaster. The trough is the lowest point of a wave, the bottom of the dip. These terms help us describe the size and shape of a wave, giving us a better understanding of its energy and behavior. Wavelength is the distance between two consecutive crests or troughs of a wave. It's like measuring the distance between the highest points of two consecutive roller coaster hills. Waveform describes the shape of a wave. Some waves are smooth and sinusoidal, like those on the surface of a calm ocean. Others are sharp and jagged, like those produced by a sudden impact. Phase refers to the position of a point on a wave cycle at a specific time. It's like taking a snapshot of our roller coaster rider at a particular moment in time. Their position on the track represents the phase of the wave. Section 5. Mechanical versus electromagnetic waves shaking things up versus lighting the way. In this section we will delve into the fascinating world of waves and explore the fundamental differences between mechanical and electromagnetic waves. Waves can be classified into two main types: mechanical waves and electromagnetic waves. Each type of wave has unique characteristics and behaviors that define how they travel and interact with the environment. Mechanical waves need a medium to travel through, like water or air. This means they rely on the particles within these mediums to propagate. Without a medium, mechanical waves cannot exist. Think of sound waves, which are vibrations that travel through the air to reach our ears. When you speak, your vocal cords create vibrations that move through the air, allowing others to hear you. Electromagnetic waves, on the other hand, can travel through the vacuum of space. This is because they do not rely on a medium. Instead, they propagate through the oscillation of electric and magnetic fields. They don't need a medium. This unique property allows electromagnetic waves to travel vast distances across the universe, reaching us from distant stars and galaxies. Light is an electromagnetic wave, and it travels to us from the sun through the vast emptiness of space. This journey takes approximately 8 minutes, covering a distance of about 93 million miles. Understanding the difference between these two types of waves is crucial for understanding how energy travels through our world and beyond. Whether it's the sound of music or the light from a distant star, waves play a vital role in our perception of the universe. By studying these waves, we gain insight into the fundamental principles that govern the behavior of energy in various forms. Section 6. Radio waves, infrared and ultraviolet light. The electromagnetic spectrum's greatest hits. The electromagnetic spectrum is a range of all possible electromagnetic radiation. It's like a giant keyboard, with each key representing a different type of electromagnetic wave, each with its own unique frequency and wavelength. Radio waves have the longest wavelengths and lowest frequencies. We use them for communication, broadcasting radio and television signals. Infrared waves have wavelengths longer than visible light but shorter than radio waves. We feel infrared radiation as heat. Ultraviolet light has wavelengths shorter than visible light. It's responsible for sunburns and is used in tanning beds. Section 7. Progressive, transverse, and longitudinal waves. 3 ways to move a crowd. These 3 types of waves are fundamental concepts in physics and can be observed in various real-life scenarios. Progressive waves are those that travel continuously in a particular direction. They can be seen in water waves, sound waves, and even light waves. They're like a conga line, with each person representing a point on the wave moving together in unison. Imagine a group of people dancing in a line. Each step they take represents the movement of the wave. Transverse waves are those in which the oscillations are perpendicular to the direction of wave propagation. This type of wave is common in electromagnetic waves such as light and radio waves. Imagine shaking a rope up and down. The wave travels along the rope, but the oscillations are up and down. This is a perfect example of how energy is transferred through the medium. The wave travels along the rope, but the oscillations are up and down. This perpendicular movement is what defines transverse waves. Longitudinal waves are those in which the oscillations are parallel to the direction of wave propagation. These waves are typically found in sound waves and seismic P waves. Think of a slinky being pushed and pulled. The coils of the slinky move back and forth in the same direction as the wave travels. The wave travels along the slinky, and the oscillations are also along the slinky. This parallel movement is characteristic of longitudinal waves, making them distinct from transverse waves. Section 8. Compression, rarefaction and stationary waves, squeezing, stretching and standing still. Compression and rarefaction are terms used to describe the regions of high and low pressure in a longitudinal wave, respectively. In our slinky example, compression is where the coils are squeezed together, and rarefaction is where they are spread apart. Stationary waves, also known as standing waves, are formed when 2 waves with the same frequency and amplitude travel in opposite directions and interfere with each other. They appear to be standing still, with points of maximum displacement called antinodes, and points of zero displacement called nodes. Section 9. Reflections, refractions, diffraction, and interference. Waves on the move. In this section, we will explore the fascinating behaviors of waves as they travel through different mediums and encounter various obstacles. Waves are all around us, and understanding their movement can help us grasp many natural and technological phenomena. Waves don't always travel in a straight line. They can take complex paths depending on the environment they move through. This non-linear travel is influenced by several factors, including the medium's properties and the presence of obstacles. They can be reflected, refracted, diffracted, and they can interfere with each other. Each of these behaviors demonstrates a unique aspect of wave dynamics and can be observed in various real-world scenarios. Reflection occurs when a wave bounces off a surface. This is a common phenomenon that we encounter daily, whether we realize it or not. Think of light reflecting off a mirror or sound echoing off a wall. These are classic examples of wave reflection. When light hits a mirror, it bounces back, allowing us to see our reflection. Similarly, when sound waves hit a hard surface, they bounce back, creating an echo. Refraction occurs when a wave changes direction as it passes from one medium to another. This change in direction is due to the wave's speed altering as it enters a different medium. This is why a straw appears bent when placed in a glass of water. The light waves slow down as they move from air to water, causing the straw to look like it's bending at the water's surface. Diffraction occurs when a wave bends around an obstacle or spreads out after passing through an opening. This bending and spreading allow waves to navigate around barriers and through gaps. This is why we can hear someone talking around a corner even if we can't see them. The sound waves bend around the corner, allowing the sound to reach us despite the obstacle. Interference occurs when 2 or more waves interact with each other. This interaction can lead to various outcomes depending on the wave's phases and amplitudes. They can either reinforce each other, known as constructive interference, or cancel each other out, known as destructive interference. Constructive interference happens when the crests of 2 waves align, amplifying the wave. Destructive interference occurs when the crest of one wave aligns with the trough of another, reducing or canceling the wave's effect. Understanding these interactions is crucial in fields like acoustics, optics, and even quantum physics, where wave behavior plays a significant role in the phenomena we observe. Section 10. The importance of understanding wave properties from music to medicine. Understanding wave properties is essential in many aspects of our lives. In music, waves are responsible for the sounds we hear from instruments. In medicine, ultrasound waves are used to create images of the inside of the body. From the colors we see to the technology we use, waves play a vital role in our understanding and interaction with the world around us. Section 11. Conclusion. Waves everywhere. Waves are everywhere, from the smallest ripples in a pond to the vast expanse of electromagnetic radiation that fills the universe. Understanding the properties of waves allows us to appreciate the beauty and complexity of the natural world and to harness their power for communication, technology, and exploration.